Good afternoon, ladies and gentlemen. Welcome to Bruker Nanosurfaces Metrology webinar. Thank you very much for your time and joining us today for thin film characterizations applied in semiconductor industries. My name is Yu Thing and I would be hosting today's webinar. Before we commence, we would like to share that all attendees would be on listen-only mode. There is an opportunity to interact with us and we encourage you to ask questions in the questions window. There will be a presentation followed by Q&A, which our speaker will answer at the end of his presentation. If we are unable to respond to all your questions due to time limitation, we will respond to you through email. Without further ado, let me introduce our speaker for today, Dr. Paljan Wei. Dr. Wei is an application scientist at Bruker, responsible for application development and technical support of nanomechanical, nanotribological, and nanoindentation instruments. His academic background was in mechanical engineering and nanometrology. Dr. Wei obtained his PhD at National Cheng Kung University, Taiwan, majoring in nanomechanical properties of thin solid films. Prior to joining Bruker, Dr. Wei was an assistant professor at the Nanotechnology and Microsystem Institute. He has published over 30 peer-reviewed international journal papers and has presented at many international conferences. We now invite Dr. Wei to share with us on thin film characterizations applied in semiconductor industries. Dr. Wei, please.
Thank you, Xiaoting, for the hosting and introduction. Good afternoon, everyone. Welcome to join today's webinar for the semiconductor-related metrology of thin films nanomechanical properties. My name is Wei. Today, we will talk about nano indentation and the nano scratch from fundamental basis to application cases of thin films. I will begin from the principles, focusing on the analysis for mechanical properties at nanoscales. On the other hand, we will go through several examples to find out how nanometrology techniques play the rules for the semiconductor's trend of downsizing. For the indentation-related applications, we have hardness as an index of residual stress, modulus as an index of dielectric constant. In addition, we will go through adhesion measurements for interfacial bonding using both indentation method and the scratch method. Not only at room temperature, several high temperature applications will be involved, including adhesion measurements at elevated temperature, glass transition temperature measurements, and the coefficient of thermal expansion measurements. Let's get started. Here we introduce the method proposed by Oliver and Farr in 1992, which is commonly used in nano indentation. There are two key steps in Oliver and Farr method for the key value of projected contact area. One is the estimation of contact depth, and the other one is the tip geometry of area function. Assuming sync-in happened at the sample at the contact with the indenter, the method uses the onset tangent of the unloading curve together with a correction factor epsilon to estimate the contact depth HC. Once we know the contact depth, we need to know more about the tip geometry. We need a function that gives information about the indenter projected area for each depth of penetration. Once the penetration contact area A sub C is determined, the hardness is simply the maxima load P maxima divided by the contact area. On the other hand, the reduced modulus ER can be also calculated using the unloading slope S and the projected contact area. Therefore, the concept of one single test for one set of mechanical properties, one is elasticity and the other one is plasticity, is shown here. One biggest difference between nano and the macro test is highly local stress strain can be achieved and highly accurate positioning can be done. With the similar concept of one test for one set of results, we are able to collect one set of mechanical property from one single nano indentation. The elasticity is reduced modulus, and the plasticity is hardness corresponding to the Young's modulus and the yield stress that one uniaxial test can provide. By using in situ SPM scanning probe microscope imaging, we can utilize the same probe used for nanomechanical testing to image the sample surface and obtain high-resolution images from which one can identify and specify the testing locations. It is very important to navigate around a sample about the microstructures and then to avoid roughness before performing nano indentations. On the other hand, after indenting, we can also go back and re-image the sample surface to verify correct indent location. Once the post-image of the indents has been performed and the precise indent location has been confirmed, we can have high confidence that their quantitative data is reliable. Here we go to the first example of indent array for observation of distribution of mechanical properties. The sample is a bump and pad system, mounted well and polished well. The bump was totally mounted, and the surface for testing is mainly the pad structure, including the two intermetal layers, feeder between the two intermetals, and the compound of the sublayer. In this case, 3 indent arrays were stitched together to form a mapping area of 40 microns by 120 microns. We can see the lower hardness and modulus of the feeder and the higher modulus of the two intermetal layers. On the bottom, the features of the base compound are also clear at the corresponding location. One interesting point in this case is that the maps show the distribution of the buried bump, especially for the modulus map. It is due to both the larger volume of elastic zone and the bigger gap of modulus between the bump and the mounted material of epoxy. The indentation measurement contains information about the deformed volume. Therefore, indenting into a sample is potentially capable to detect the information of underlayer. Since the indentation measurement contains information about the deformed volume, indenting to a film substrate sample is capable to detect the information of both the film and the substrate. When the applied load is small enough, the penetration depth is small and the deformation zone could be within the film. In this situation, the collected mechanical properties could be contributed by the film only. When the applied law increases, the indenter goes deeper and deeper, and thus the deformation zone gets bigger and bigger. A substrate effect is observed when the deformation zone reaches the substrate. In this situation, the collected hardness and modulus are contributed not only by the film but also by the substrate. There is a transition of hardness and modulus changing with the penetration depth. At small depths, the film properties dominate, and at large depths, the substrate properties dominate. Typically, the 10% rule is general approximation for film's intrinsic mechanical properties. That is, we will collect the small depth data with the penetration depth smaller than 10% film thickness. As the films become thinner and thinner, the elastic deformation reaches the substrate at very shallow depths, and it can be very difficult to make measurement without any substrate influence. Here shows one of typical cases of substrate effects. The sample is micropads. There is one data set of hardness and modulus changing with the penetration depth we called depth profiles. Two transitions show in the depth profile of hardness on the top and the modulus on the bottom. The depth profiles indicates the top layer of the micropad has lower hardness and lower modulus compared to the under layer. Following the 10% rule for the intrinsic mechanical properties, the film's intrinsic property were found to be stable values at a small penetration depth. That is, the hardness is around 0.9 gigapascal, and the modulus is around 83 gigapascal. Before going to the next application of micropad, let's take a look at the orientation effect in copper's modulus, because copper is the common material for pad. Copper's modulus is highly sensitive to orientation. We know copper has the structure of phase central cube, and there are three main orientations: 100, 110, and 111. Theoretically, the three orientations have very different modulus values due to the different atomic density. However, traditional tests cannot differentiate the modulus if the deformation zone or deformation size is larger than the average grain size. The three modulus values can be only detected separately using the true nanoscale measurements. As reported on the left chart shown here, the penetration depth goes down to several nanometers, and at this shallow depth region, these three orientations have clear different modulus values. Here we demonstrate an example of micro copper pad with a square cross-section of 15 micron times 15 microns. Within the cross-section, an indentation array of 15 by 15 indents were performed at room temperature. After that, we have modulus map with the corresponding histogram shown here. There are two portions shown in the modulus map of the cross-section. The left portion has higher modulus, and the right portion has lower modulus. Comparing the two peaks showing in the histogram, one is around 60 gigapascal and the other one is around 120 gigapascal. Comparing with the two peak values with the three orientation modulus of copper mentioned previously, it is easy to figure out the lower one is 100, and the higher one is 110. That is, we can assume that only 2 grams exist in the cross section of the micropad, and one is 100, the other one is 110. There is an example about challenges due to downsizing. When the size is down to grain size, the uniformity issue will happen since the copper pads are not that polycrystalline anymore. Now we are going to the first application of indentation, the residual stress. Let's take a overlook at the scales and the metrology techniques of coatings residual stress. A lot of reports show that the performance of semiconductor materials is highly sensitive to residual stress. Therefore, residual stress is always an important factor for semiconductor materials. Residual stress is a multi-scale problem, and this slide shows a classification of 3 types of 3 scales. There are 3 different metrology techniques corresponding to the 3 types of residual stress. Type 1 is the macro residual stress, which is global stress over the entire wafer. The technique for type 1 residual stress is warpage method, which needs measurements of curvature. And the type 3 is atomic scale residual stress due to the crystalline defects. The technique for type 3 is X-ray diffraction method, XRD. Between them, the type 2 residual stress is a micron scale, and the technique is indentation hardness, which is what we are going to. Indentation hardness is sensitive to residual stress within the tested sample. Compressive residual stress was found to linearly increase the indentation hardness, and the tensor stress does in the opposite way. Therefore, indentation hardness can be used as an index of residual stress. Here, we have 2 wafers of 1 micron silicon oxide films undergoing different treatments. The type 1 stress was measured using the warpage method, and the value of stress is shown here. Wafer 14 has higher compressive residual stress compared to wafer 13. Since we have the 9 indentation tests collected from each wafer and the low depth data shown in this plot. Since the repeatability is very high, we can clearly see the penetration of wafer 14 is smaller than that of wafer 13 at the same peak force. It indicates the wafer 14 has higher hardness, which is due to its higher compressive residual stress. Another indentation application is modulus as an index of dielectric constant. The sample is a low dielectric constant film, called a low K film for short. Typically, low K films are porous in order to get lower dielectric constant, and the UV curing is one of important processes. Since both dielectric constant and the modulus were found to related to porosity, positive correlations was reported between the dielectric constant K and the modulus. Therefore, higher modulus corresponds to the higher k, and lower modulus corresponds to lower k. This concept will help us to do the main purpose of this work, which is to figure out the dielectric constant distribution in thickness direction and check the vertical uniformity due to the UV carrying. In this case, we used the scanning wire as nanomachining to remove the low K film by 40 nanometer and 80 nanometer at one pass and two passes respectively. After that, we carried out modulus mapping to get the idea of modulus on the top surface, the 40 nanometer depth surface, and the 80 nanometer depth surface. And the modulus line scan is showing on here. The original surface has the highest modulus of 33 gigapascal, which indicates the higher dielectric constant existed on the original surface. After that, on the 40 nanometer depth surface, the modulus is around 18 gigapascal. And at the 80 nanometer surface, the modulus is only 8 gigapascal. It is like a half modulus on 40 nanometer surface and another half modulus on 80 nanometer surface, which indicates the lower and lower dielectric constant. The results show that the low K film has higher stiffness and thus a higher dielectric constant on the top surface, on the original surface. And the depth dependency is so significant in thickness direction. Let's go back to take a look at the scanning wire in detail. Based on the in situ scanning probe microscope SPM, nanowire can be done by setting scanning load at different levels. In addition, the number of passes is also a useful parameter for nanowire. After finishing nanowire with the set force and the number of passes, the post image can be collected using the in situ SPM to quantify the wire volume. It is not only for nanomachining shown in the previous case, but also powerful to measure wire resistance directly. Here we have the application cases with three different hard coatings, and the wear resistance is the tribology property for investigation. In this case, we select three different applied loads from 50 micronewton, it's micronewton, to 200 micronewton. No matter the applied load is high or low, sample 3 was found to have smaller wear depth compared to the other two, which suggests better wear resistance. One emphasized point here is that even at the lowest force of 50 micronewton, the residual depth is smaller than 1 nanometer. The high sensitivity of nanowire is still capable for differentiating the wear resistance of the three samples. Now we are going to the topic of interfacial bonding or adhesion measurements. Since the number of thin films existing in semiconductors is huge, the number of interfaces is also huge. Therefore, the interfacial bonding is one of important properties for thin film industries. Here shows a variety of metrology techniques for adhesion measurements. The common point is applying load to delaminate coating from substrate. Some techniques need to specify sample preparations, and some needs ex situ measurements. Among all of these techniques, nano indentation and the nano scratch are really suitable for thin films due to two main advantages. One is direct measurement, which the probe can be directly applied onto the sample surface without any preparations. And the other advantage is high spatial resolution. Typically, the 1 nano scratch length is at micron level, and the nano indentation is at submicron level. Therefore, a large number of tests can be performed on the entire wafer, and it is very useful for distribution check or the uniformity check. Here we go the first adhesion application using nano indentation. The sample is thin nitride film on copper. The main challenge here is the sublayer of copper is polycrystalline and has grain boundaries. The nitride top layer film is so thin that the copper's grain boundary cannot be fully buried. In this situation, the in situ SPM is very useful for detect the surface texture of grain boundaries. We can see the average grain boundary grain size is around several microns. Therefore, there are about 10 grains existed in one SPM image with a 10 micron scan size. After having the pre-scanned image, it is convenient to choose suitable location within grains to avoid making indents on boundaries. Therefore, we can also have the post image after making indents to make sure all indents are made on the specific size that we set. Since we are able to ensure all indents were within grains, the information of indentation is nothing about the boundaries. They are popping events happens in all indents, and they are signals of delamination between the nitride thin film and the copper. The mechanism of indentation-induced delamination is shown here. When indentation load was applied into nitride film, the in-plane stress increased, and at the critical point, the interface debonds. In this case, the loss at the biggest pop-in events was picked as the critical load, which is an index of adhesion. On the other hand, we also applied nano scratch to measure the nitride copper adhesion. The nano scratch test is quite flexible and can be set up in a number of ways, but there are two main categories of tests usually employed. In a scratch test, the lateral axis is always operated in displacement control feedback, so the user specifies a scratch length and the speed. In the normal axis, it can be operated either in the load or displacement control, but load control is more common. A ramp force scratch test is probably the most common type for testing the film's adhesion. During this type of test, the normal force is increased continuously when the probe moves laterally. As the probe penetrates deeper and deeper, increasing stress is placed on the probe and the substrate interface. And at a certain point, the interface fails and the fin delaminates. If the fin are brittle, Some events such as cracking or chipping may also be observed. Let's go back to the thin nitride film on copper case. We have to deal with the grain boundary problem for the scratch test also. One of the helpful thing that we can do is set a pre-scan segment for nano scratch test. Before scratch, the probe was moved along the path with a small contact force of around 1 or 2 micron Newton. The normal displacement of data for the pre-scan segment are useful for both tear correction and the line scan profile measurement. Since the measurement path is exactly the same as the scratch path, it is useful for observation of the surface, text, and roughness effects. And here, we will use the pre-scan data for grain boundary observations. From the pre-scan data, we can see the grain boundary was detected during the path of 10 micron length and 2 grain boundaries was detected. After that, we made a reinforced scratch going through the same path, and the results were shown here. You can see the normal force increased linearly as it has been set. And there are 3 signals showing both lateral the lateral force signal and the normal displacement results. Since we have the pre-scan data of the line profile of the scratch path, and the direction of pre-scan is opposite to the direction of the scratch. Therefore, all we have to do is to use the reverse of line scan profile for checking the locations of the grain boundaries. Therefore, the first 2 signals are clearly recognized to be induced by passing the grain boundaries, and the third one signal is the signal due to the delamination. Therefore, we can judge the critical point as the third pop-in and pick the normal force as the critical load. Since we collect the critical load results using both the indentation method and the scratch method, the comparison is available. Here we put the scratch critical load in the x-axis and the indentation pop-in critical load as the y-axis. A linear relationship was found between the critical loads collected from the 2 methods. That indicates both of these 2 indexes are suitable for adhesion measurements in this case, and we can actually convert one to another using this formula. Not only for the film sample, nano scratch is also useful for adhesion measurements for bump and pad samples. The first mode shown here is making scratch from the top cap of microbump. At the beginning, the probe was indented into the bump, which penetrated through the cap there with a applied load. After that, the normal force remains constant and the probe starts to move laterally. One of the possible failure mode is shown here, that the rupture of the underpass layer shown here. So this is the advantage of the in situ SEM scratch test. We can directly see the delamination of the underpass layer. Actually, we can perform some examples of testing in different directions. We can check the collected lateral force and pick up the critical values with the bump is pushed down. One by one bump test can provide the distribution of the interfacial bonding of the under passivation layer. Not only investigation for the uniformity, we can also set scratch tests in different directions to see the isotropic effect. The most significant feature of this mode is the crack of passivation under there, which can be found on the touch surface on the opposite side of the scratch direction. Besides the scratch from the cap, another scratch mode that we can perform is direct push from the side wall using a special wedge tip. Shown here, we can land the probe next to a bump and push it from the side wall. Due to the high sensitivity and the low noise floor, the probe can be landed with very small contact ratio. On the other hand, a lift height can be set to achieve different failure modes. And we can see the differences between the modes via the post image of the bump. Large number of one-by-one tests provide statistic measurements and make the distribution investigation possible. Now we will go to another application case of adhesion, which is also a direct push from the side wall, but the entire test is performed in SEM. This is a beautiful work done by one of Japan users of in situ tools. The interface is between copper and the passivation layer of nitride and oxide, which is used in semiconductor devices shown here. And the main topic is how orientations of copper affect the interface bonding. The idea is to finish all tests in one SEM chamber. Therefore, the sandwich structure of sample was designed to be the passivation layers as the top layers and the copper layer as the under layer. The first step is using FIP to create micropillars of passivation standing on different locations of copper surface. After that, use the probe to push the micropillars from the side wall and collect the force required to push down. In order to turn the critical load into the adhesion work, a final element method was established, shown here. Finally, the copper surface was moved to the EBSD gun for orientation measurements. The results are shown here, which suggest 100 has the highest adhesion work and the strongest interfacial bonding was found in this orientation of 100 compared to the other two orientations. Once the sample, let's recall the entire steps of this beautiful one-chamber design. Firstly, once the sample of sandwich structure gets into the SEM with PI88 stage, with the stage of orientation and tilt, everything's ready. First of all, we move the sample to flip gun to create the micropillars, and then move the pillars to the probe for direct push from the sideward. Finally, move the sample surface to EBSB gun for orientation measurements. Therefore, it is so smart and so efficient to get all necessary measurements done in one SEM chamber. Now we are going to high temperature test. In a lot of cases measurement, the properties at room temperature is one thing, and measuring properties at different temperature is another story. Properties at different temperature are always interesting and important. First of all, let's take a look at the main add-on needed to achieve high temperature test, the exo stage. Several features are listed here, and I would like to emphasize three of them. The first one is uniform sample temperature, and the second one is for pro-tip heating in uniform environments, and the third one is the easy sample mounting. Let's go in detail of these three features. The heating stage, exo stage, has two heaters designed to clamp the sample in the middle. The sample is under temperature control on both two sides. Therefore, the temperature within the sample can be highly uniform. Moreover, the unique engineering chamber design allows to minimize the influence of environments and maximize the stability of temperature control. The minimal exposure of the sample reduces the distribution, therefore limiting its influence to the instrument itself. The tip on the long shaft is designed to go into the chamber through the hole of the top heater. Therefore, the tip can be heated to the same temperature before going contact with the sample surface. Of course, dynamic testing capacities are also available. On the other hand, no glue is needed since the heaters are designed to clamp the sample. It is a significant advantage because glue could be a big problem, especially at very high temperature. Let's get the indentation method for adhesion to be the first high temperature application. The sample is an ultra low K film on silicon, and a cube corner indenter was chosen to induce cohesive and adhesive failure. Similarly, popping events were picked up, and the force at popping events is detected as the critical load. Here we will focus on the cohesive failure at different temperature. With the exo stage, the temperature can be set up to from room temperature up to 300 and 400 degrees. The pop-in events can be detected at different temperature levels, and the critical point was found to increase when the temperature went up. The increase of critical load was found to be linear to the increase of temperature, and the slope is around 0.28 micronewton per degree. It is related to the in-plane stress linearly changed with the temperature due to the CTE, the coefficient of temperature of thermal expansion mismatch between the low-K film and the silicon substrate. Therefore, it suggests the possibility of detecting CTE of the low-K film since the silicon, the CTE of silicon is well known. I would like to skip the details of calculation for the film's CTE. You can find out the details in this published paper. Here we simply get the idea of indentation method for adhesion or cohesion measurements can be done at elevated temperature. Another similar example of indentation-induced delamination is shown here. The sample is a polymer film on copper sublayer. The temperature was chosen to be lower than its glass transition temperature of around 250 degrees Celsius. Therefore, the three temperature levels are set here from 35 to 215 degrees Celsius. And with the same peak force applied using the same indenter, the penetration depth clearly gets larger and larger at the higher temperature. And the pop-in events happened at a smaller critical load at higher temperature. If we choose a peak load smaller than the critical load and follow the 10% rule to avoid the substrate effect, the intrinsic mechanical property can be measured as shown in this list. As temperature went up, both hardness and modulus were found to be decreased. Therefore, both critical load and hardness modulus of the film decreased when the temperature went up. Talking about the glass transition, dynamic mechanical analysis (DMA) is one of the commonly used technique. DMA measurements can provide three judgment rules for glass transition temperature, TG for short. One is storage modulus onset, and the other two are loss modulus peak and the 10 delta peak. Compared to the rule using storage modulus onset, it is easy to apply the rules of peaks for determination of TG. One point needs to be emphasized here is that glass transition is actually a band of temperature, not really a temperature point. And the DMA measurements provide an advantage of three observations for glass transition. We can see the storage modulus onset suggests the beginning of the glass transition, and the loss modulus peak happens at the middle of glass transition. Finally, the TG peak is the end of the glass transition. Therefore, using DMA at different temperature levels, we can get the full information of glass in transition. Here we have the comparison of TG measurements of a 500 micron thick PDMS, and the judgment rule is 10 delta peak. We have two sets of DMA results at the same temperature range and the frequency level, but at different scales. One clear advantage shown here is the convenience of direct measurements for thin film samples. For this case, with the thickness of 500 micron, it is not that difficult to put the PDMS sample and fix it for the macro testing. However, in case of the thin film case, nano DMA could be of much help since the sample can put directly in the heating stage and to make dynamic indents on it. Let's go to an example show how nano DMA is working for thin films. Here demonstrate the TG measurement results, and the sample is 1 micron polymer film on silicon substrate. DMA indentations were applied to the sample in order to collect the storage modulus, and 10 delta vary with temperature. And the axial stage were used for controlling the sample temperature from room temperature to 260 degrees Celsius. The results shown here and the top is the storage modulus, and the bottom is the 10 delta. The result shows a 10 delta peak happen at the temperature of 210 degrees Celsius, which indicates the end of glass transition. On the other hand, the onset of storage modulus happened at 120 degrees Celsius, which indicates the beginning of the glass transition. These two temperature points suggest the glass transition had a bandwidth of around 90 degrees. Another point we can see is that the storage modulus before Tg is around 5 gigapascal, and after Tg it drops to around 0.5 gigapascal. It is a typical observation of going through the glass transition. The final topic of heating high temperature measurements is the coefficient of thermal expansion CTE. Here we have the definition of linear CTE shown here, which is the ratio of the size change to the original size divided by the temperature change of delta T. The left-hand side is the list of CTE values for materials typically used in semiconductors, including the silicon of a CTE with a CTE of 2.6 ppm per degree, and the copper with a CTE of 16.7 ppm per degree. Today we have a case of polymer used as underfill, which has a reported region of CTE from 50 to 200 ppm per degree. Similar to TG measurements, the main advantage of direct measurements is so significant for films CT measurements. The 4 steps shown here to how nanowire together with in situ SPM works for the CT measurements. The first step is using the scanning wire to remove top layer, just like the previous case about the module's distribution in thickness direction. And the removal is not necessary to be 100%. The key point of the first step is to create a height difference within the film. After that, we collect the image of nanowire, including the warmed region and the original region. And the third step is to repeat the in situ SPM at different temperature levels. Finally, the depth change of the warm region, or the height difference between the warm and the original regions, is related to the temperature change. And then we can analyze the depth change with the temperature change to determine the CT using the linear CT definition. This is the slide showing an example of this method. The sample is a polymer film with a thickness of 5 micron used as underfill. Firstly, a warmed region was created at room temperature, and the depth is around 1.5, 1.6 micron at the beginning. And then the in situ SPM was performed at different temperature level from room temperature up to 200 degrees Celsius, which is slightly below its TG. And the depth versus the temperature results shown here, we can find a linear relationship between them, and thus a linear fit can be easily conducted. The slope was found to be 0.35 nanometer per degree, and then the CT can be calculated to be 224 ppm per degree. The warm region is only a 10 micron square, and the poster image has the size of 50 micron by 50 micron. Therefore, this method has very high spatial resolution. It is potentially possible to repeat the measurements crossing the entire wafer and gets the CT distribution in the wafer viewpoint. This is the final takeaway slides. All the applications we present today are based on the 4 core techniques of high-strung instruments. The main advantages of thin film application are direct measurements, high spatial resolution, and easy index. Except the in situ SEM cases and the high temperature cases, all other applications are based on full wafer basis. I believe all today's application cases are potentially helpful for the R&D team and the quality control team, process control team, and the failure analysis teams. This is all the presentation for today's webinar. Thank you for your attention, and I will go to the question and answer and the question segment, and I will do my best to answer the question. Okay, let me see. Okay, I will pick up this one to answer. Okay, for thin film characterization, if the fin is very thin, like less than 100 nanometers, there is no flat region, possibly no flat region for modulus at the beginning of very shallow depths. And in this case, how to get the fin only property that means intrinsic properties from the indentation test. Okay, for this, this is a very good question. For this kind of a situation, when the fin has a extreme or ultra thin thickness, we will recommend users to use a numerical method based on the depth profile data we call the ITF solution, which is one of high-strung products. And the ITF is intrinsic thin film property, which is a calculation software for calculate or determine the intrinsic modulus at the ultra shallow depths where the real data could be not so reliable, or in this region the uncertainty could be very high. So we will apply the raw data of depth profile into this ITF calculation to get the intrinsic property of thin film, of ultra thin films. Okay, the other question is in the test of copper pad, the indentation depth is quite low. It's only several nanometers. In such low indentation depths, how to do the tip calibration? It means the area function calibration. How you convert the hardness difference to stress in megapascal. Okay, maybe I will give the problem here, the question here. Typically, with the noise flow of our transducer, typically I will able to calculate the tip geometry function, or so-called area function, down to 2 nanometers, maybe 1 nanometer is also available. Therefore, the example that you see for the copper pads, it is not difficult to me to get the penetration of several nanometers. I mean, the calibration can be achieved down to 1 or 2 nanometers. For me, it is quite a common situation I can guess. Okay, I guess I didn't get the point of this another problem. The question about converting hardness difference to stress in megapascal, because the according to the reports, the uh, dependency of hardness to the stress is 100% linearly. I mean, if the compressive stress, implant stress is 1 gigapascal, then the indentation hardness will be higher by 1 gigapascal. Therefore, because gigapascal is just simply 1000 megapascal, therefore I think it is quite easy, quite direct to convert the hardness difference to the residual stress in no matter a unit of megapascal or gigapascal. Okay, due to the time limitation, I guess I need to go to an end at this moment. And thank you for your attention. And I will hand the floor over back to Shooting. Thank you, everybody.
Thank you very much, Dr. Wei. Ladies and gentlemen, that concludes our webinar for today. We hope you have found it informative and helpful.